through a few logistics notes. So there is an extra TensorFlow review session that Josh is going to be leading, so all the information about that is on Piazza. And homework 2 is due 1 week from now, so hopefully all of you have handed in homework 1 already, and then homework 2 will be due next week as scheduled. So do get started on that early. Make sure that you take the opportunity to go to office hours if needed and so on. And again, remember to start forming your final project groups. All right, today's lecture. Today we're going to build on the stuff that we covered on Monday and think about the case where you might have just a critic without an actor. So this notion of learning value functions, somehow it seems like that value function contains a lot of information about what actions are better or worse, and maybe we could actually dispose with the actor completely and just use value functions to choose actions. So that's what we're going to discuss today. We're going to talk about how we can extract a policy from a value function, and then we'll work our way through the Q-learning algorithm. We actually won't do extensions. We will do those next week. Today we'll actually cover some theory instead, so that's a little error. We'll cover theory of value function learning. The goals of today's lecture will be to understand how value functions give rise to policies and how we can actually obtain policies just by learning value functions, understand the Q-learning algorithm, and then also understand a few theoretical details that allow us to understand what it is that Q-learning and value function learning algorithms are really doing, and in which situations can we expect them to work well. All right, so let's very briefly recap what we covered on Monday. We went through the actor-critic algorithm, a few different variations of the actor-critic algorithm, and all of these algorithms basically have the following general scheme. We're going to generate some data, just like in any other reinforcement learning algorithm. That's in step 1. Then we're going to fit some kind of critic to the data that we gather to estimate the value of the current policy from different states. And usually the way that we do that in deep reinforcement learning is that we fit a neural network to the value function. And then we're going to use this fitted value function to estimate the advantage function, which tells us how much better each action is than any other in any given state. And then once we have the advantage function, we can combine that with a policy gradient so that we can compute a gradient that allows us to actually improve our policy. So this is the high-level sketch of all of the variants of actor-critic that we covered on Monday. So if we're learning these value functions, is there some way that we can just omit that policy gradient completely? Like, that policy gradient is kind of nasty. It has very high variance. We went through a lot of trouble to try to get it to be better and better. Maybe we could just get rid of it. Here's the slide, how we can kind of work towards that. The advantage function, which we already know how to compute, that's what we covered on Monday. The advantage function tells us how much better a particular action A is than the... Could we do this after the lecture?
The slides is not showing.
The slides are not showing on the live stream? Okay. Yeah. So should I try to switch to that? No, it's a little more colorful than I'd expected. It would be nice to have kind of more traditional colors. Could be something is wrong with the VGA cable?
It's brand new.
Okay. I don't have a VGA dongle with me. I do have an HDMI dongle, but you said that with the HDMI it wasn't showing up on the recording?
Yeah. This is a
I see. So it's probably on the other end of the machine. Is there any way to have this go through anything other than VGA?
No. Actually, my camera's not responding.
Well, if the only way we can record it is like this, we'll have it be in garish colors. How's that? And then maybe we can get it fixed for next time?
Yeah.
Okay.
Someone in the audience has a VGA dongle.
It's not. I think it's not the dongle. I think it's on the other end, actually. Okay, so unfortunately we'll have some very bright colors for today, and this is in order for the people watching online to actually be able to see it, because apparently the slides aren't showing up otherwise. So, you know, it'll be a little more festive today. That's okay. I won't have any cool videos anyway, so I think this is actually fine. Well, your eyes will adjust after a while. Okay, so for everybody watching online, I'll just recap what I was saying there, since you guys didn't see the slides. So the question that we're going to study today is, can we omit the policy gradient completely? And to get started thinking about that, let's think about what the advantage function actually tells us. So all the actor-critic algorithms that we discussed on Monday, they all estimate an advantage function somehow. And that advantage function tells us, in any given state, for any given action, how much better is that action than the average action according to pi. And that's a very, very useful thing to know. If we know for every action how much better it is than the average action according to pi, then if we take the action that's best according to the advantage function, if we take that action, that'll give us the best possible value we can get if afterwards we're going to follow pi. So in particular, that means that taking the action AT that maximizes the advantage is at least as good as any action that we'd get by actually sampling an action from pi. And that's actually regardless of what pi is. So for any pi, if we can estimate the advantage a pi and then take the action that maximizes that advantage, that action will be at least as good as whatever we would have gotten from pi. And that means that this is a mechanism for policy improvement. So let's forget policies. Let's just do this. Let's just always choose our action by maximizing the advantage. So we can write down the policy that this corresponds to. It's actually very straightforward. It's just a policy that assigns probability 1 to the action that maximizes the advantage at that state, and probability 0 to all the other actions. And since we know that this action will be at least as good as the action that we got from pi, that means that if we estimate a pi for some policy pi, and then switch to using pi prime, that'll be a better policy. So we'll have achieved policy improvement. So then we can repeatedly do this. We can essentially keep estimating the advantage of each policy, build a new policy that takes the action that maximizes the advantage, and repeat. And in this way, we can get better and better policies. And this is actually the underlying idea for basically all of the algorithms that we'll cover today. So this pi prime is at least as good as pi, and probably better. So then the high-level scheme of all of these value-based reinforcement learning algorithms will be that in the, ooh, that's not a green box. Oh, man. In the top right box, they're going to fit the advantage function. In reality, they might actually fit the value function or the Q function, from which we can compute the advantage, as we discussed on Monday. And then in the blue box, they'll just, that is blue, right? In the blue box, they'll actually use this rule over here to build a new policy. Build a new policy pi prime, and then replace the old policy pi. OK, so this is sort of the high-level outline, and then we'll go through a few specific instantiations of how we can do this in practice. All right, so to begin with, we'll actually take a step back and we'll describe algorithms that operate under substantially simpler assumptions than the ones that we typically focus on in this course. We won't deal with neural nets. We won't deal with unknown dynamics. We'll actually just assume that we know everything. We know the transition dynamics, and the state space is small and tabular so that we can actually just use a big table of values instead of a neural net. So we'll just simplify and derive a few basic foundational algorithms, and then we'll make them deep afterwards. So the first and kind of simplest approach that I'll describe that does this is called policy iteration. And the high-level idea in policy iteration, exactly what I said on the previous slide. Step 1, evaluate the advantage of the current policy pi. Step 2, improve the policy by using that argmax trick, and then repeat. So you set pi to be this pi prime, which assigns a probability of 1 to the best action according to the advantage, 0 to all the other actions, and then you repeat. So then the big question that comes up is, how do you do the step 1? Because step 2 is obvious. Like once you know everything, once you know the advantage, just set your policy like this and you're done. So the main question here is how to do step 1. So as before, when we talked about actor-critic algorithms, we're faced with this choice. You have three different objects. You have A pi, Q pi, and V pi, and you have to figure out which of those objects should you learn. And of course, as before, the advantage is given by the current reward plus the expectation of the next value minus the current value. So let's just do the same thing that we did in Actor Critic. Let's start by trying to evaluate V pi. That's what we did in Actor Critic. We kind of know how to do that. Let's build off of that. So this class of methods is sometimes broadly called dynamic programming. And we'll just assume that for now that we know the dynamics, so we know the probability of the next state given the current state in action. We'll get rid of this assumption later, but for now assume you know it. And furthermore, we'll actually assume that both the state and the action are discrete and small. So for example, maybe we have like a little grid world. Our actions correspond to walking around in this grid world. And maybe it has like 16 states, 4 actions per state. We can store the full V pi just as a big table exactly without any approximation error. And that just corresponds to assigning a number to each of these states. And the transition matrix is just a 16 by 16 by 4 tensor. So everything is easy. And the reason that we want to assume that is primarily so that we can deal with these tabular representations of the value function. Because later on, once we start fitting neural nets to value functions, we'll get all sorts of nasty approximation errors. So for now, let's just deal with a tabular version where there is no approximation error so that we can derive the algorithm. So for now, everything is simple. And when everything is simple like this, we already know from the discussion of actor-critic algorithms that we can construct this bootstrapped update for V pi. So for actor-critic, we saw that we could use the reward plus the next value as an estimate of the value function. And of course, the value function is a function of the state. So you need to take an expectation of this whole thing with respect to the actions, where the actions are distributed according to your policy. So this gives us a way to update our value function, just like we saw in actor-critic. So the bootstrap means that in here, for the value at the next state, you'll just plug in your current estimate, your current tabular value function. And your policy has this very convenient, simple form where it just assigns a probability of 1 to exactly one action. So we can actually write it out as a deterministic policy. It's just a function of the state that gives us an action. So this expectation out here, we can actually get rid of that because we know that only one of these actions is going to have a probability of 1. And we can equivalently simplify this to just say we'll take the reward for the action given by that policy plus the expectation given the state and the action of that policy. So we've gotten rid of that outer expectation because the policy is actually deterministic. So the way that we can do policy iteration here, step 1, evaluate V pi. Step 2, update the policy updated like this, and repeat. And then the way that you evaluate V pi, which is policy evaluation, is just by repeatedly applying this recurrence. So you repeatedly set V to be the current reward plus the expectation of the next value. And if you assume you know the dynamics, then you can, of course, compute that expectation exactly. So this is an exact algorithm. There are no approximations. And in step 1, you exactly evaluate the value of the current policy. And in step 2, you exactly improve your policy. So, of course, mainly for these kind of simple, discrete environments where everything is tabular and convenient. Now, well, first of all, does anybody have any questions about policy iteration? Yes?
What about if, like, does this include like I guess you could think about a dynamic programming example where you would need to look more than 2 steps ahead, like more than 1 step ahead to like figure out what the optimal thing, like you could get a bunch of immediate reward, but then you
So this is actually a long horizon algorithm because all future rewards are being included in here. So if you imagine what this does, in 1 step, if you initialize your value to be all zeros, in 1 step the value function just gets a copy of the reward. In the 2nd step, it gets a copy of the reward plus the next reward. In the 3rd step, it gets the reward after that, and so on. So the more iterations you take, the further into the future you're going to integrate your rewards.
But how
So,
sorry, go.
No, go ahead.
But if you like knew what maximized your reward, at the next step, like I guess.
You're not maximizing your reward. You're maximizing your advantage. So the advantage is the expectation of rewards for all time steps until the end of time.
I think I'm probably getting a little ahead. But I mean, like, how do you explore the reward space is sort of what I'm.
So the assumption here is that you can compute all of these equations at all states and all actions.
Okay.
So this is why I said that we want this tabular assumption.
Okay.
So for now, we're not dealing at all with sampling error or approximation error. That'll come up later.
Right. Sorry.
Yes.
Question, why is it a 16 by 16 by 4 tensor?
So this is the probability of transitioning into any state given a state and an action. So 16 source states and 4 source actions. OK, now one thing we can do with dynamic programming is we can simplify it even further. And this is going to seem at first like a bit of a silly exercise, but later on it will actually lead to some very convenient model-free RL algorithms. So here's a thought. This argmax, this is how we compute the action to take, right? And the advantage is given by the current reward plus the next value minus the current value. Now, the argmax of the advantage is actually exactly the same as the argmax of the Q, because the current value that you're subtracting here, it doesn't affect the best action. So you can actually do a little simplification, just remove this minus v here. So you can just do the argmax on the Q. And the way that you would do this in a tabular case is you would build a big matrix where one dimension is states and the other dimension is action, and you would actually compute the Q value for every combination of state and action. If you have a 16-state grid world with 4 actions, this is pretty easy to do. So then you go through and you would highlight whatever the max in each column is, and you would write that out as your action. That's the action that you're going to take. So the argmax gives you the policy. But the value in this matrix, you can actually just take the max instead of the argmax, and the value, that actually approximates the new value of that policy. And that's very, very convenient, because now you can actually skip the policy and just compute the values directly. Like if you know that you can just take the number from here and put that into your value function, you don't actually need the pi at all. And this gives us an even simpler algorithm called value iteration. And in value iteration, we build this big table of Q values, just like we did for the policy iteration. But then, instead of actually explicitly estimating new policy pi prime, we'll just estimate the new value by taking a max over the Q function with respect to the actions. And now the policy is not even explicitly represented anywhere in this algorithm. We're just directly working off of values. So the policy is sort of implicit in the fact that you're doing this max, but you never have to build a table of probabilities. So now that the algorithm is simpler, here you just evaluate this big table of Qs, and here you just take the max over the different columns. And this is the value iteration algorithm. The value iteration algorithm is a very classic and very popular dynamic programming algorithm when you know the transitions and you have a state space that can be represented in a table that's small enough to represent in a table. OK, so now we'll actually start moving beyond tabular state spaces. So how do we represent V of S? Well, we can represent it as one big table with one entry for every discrete S. This is, in general, not a very good idea if you have very complicated problems. So you can have a value for every S. But if your S corresponds to, let's say, images in a video game, your typical video game image, maybe it's a 200 by 200 pixel image. This is not like, in reality, it would be much bigger than that. But let's say 200 by 200. We'll be modest. Each pixel can take on 255 values and has 3 color channels. So the total number of states is 255 to the 3rd power raised to the 200 by 200 power, which is more than the number of atoms in the universe. So building a table like this would require a very large data center indeed, and is generally not recommended. And this is sometimes referred to as the curse of dimensionality, and that's one of the biggest problems with kind of classical dynamic programming approaches. In fact, the term curse of dimensionality is pretty much as old as dynamic programming. So as soon as there was dynamic programming, there was a curse of dimensionality. So what can we do? Well, I think we all kind of know what we're going to try to do is we're going to fit a function approximator. You don't have to fit a neural net function, but you could. So our function approximator is going to take in the state, and it's going to output an estimate of the value. Now, this seems like a very neat idea. It's actually going to introduce a whole host of really horrible problems. But let's just go through how we can do it first, and we'll handle all the problems after the break. So you now have a parametric function approximator, like a neural net. It has parameters phi, and it's going to take in state and output estimates of values. And just like with actor-critic algorithms, we need to construct some kind of loss function so we can train it. A very natural choice for the loss, because this is a regression problem, is to use a mean squared error loss. So our targets are these max Qs, the max over the actions of the Q values. And we're going to fit the V phis, so that's our loss function. And we can write down the fitted value iteration algorithm. So in step 1, we compute our target values, just like we did with actor-critic. And now these target values involve computing the Q function here, R plus the next value, and maximizing with respect to the actions. And then when you update your neural net function approximator, you just solve this minimization problem. So you'll find the parameters phi that minimize the error between the output of the neural net and the target values. And this you can also do at samples. So if you have a very large number of states, maybe you just sample some supporting set of states. Doesn't really matter so much what they are, so long as you get good coverage, and then you minimize the subjective on those sampled states. Yes?
For a large action space, is this maximization still easy to do?
No, this maximization is really, really hard. Yeah, it's very hard. In fact, it requires knowing the dynamics of the system. So, yes?
So here you assume that the state space can be continuous, but then the action space is still discrete.
It doesn't necessarily have to be discrete. You can do the maximization on continuous actions too, it's just harder. There's actually a bigger problem with the actions, which is that you're actually assuming that you know the transition dynamics. So in order to perform this maximization over here, you need to know which action leads to which next state. And typically, if you have a model free RL algorithm that's continuously interacting with the world, maybe it can take actions in the world and see their outcomes, but it can't go back to a state and try every possible action. So if you're driving a car, you can't teleport the car to somewhere where it's been before. If you have a simulator, you can perhaps do this. So if you do know the dynamics of the system, you can perhaps evaluate this max. Maybe it's easy for discrete actions or hard for continuous actions. But if you don't have access to the ground truth dynamics, then this maximization actually can't be done because it requires trying different actions in the same state. So when we switch to fitted value iteration, we lifted the assumption that the state space is small and discrete, but we still have the assumption that we know the dynamics of the system. And that assumption is rather restrictive. So we need to know the outcomes for different actions. So let's try to get away from that assumption also. And to get away from that assumption, we'll first go back to regular policy iteration, and then we'll make the switch back to removing the policy and putting in the max. So if we go back to policy iteration, remember that you can maximize advantages or you can maximize Q values. They're the same thing because they differ by a factor that doesn't depend on the action. So let's actually mix it up a little. Let's say our policy iteration now is going to evaluate Q instead of A. It's basically the same, right? And then step 2 will improve our policy exactly the same as before by setting it to be probability 1 if the action maximizes the Q and 0 otherwise. So we're all good with the same policy iteration as before. And now what we'll change is we'll change this step 1. We'll change how we compute this Q. Instead of computing Q by repeatedly estimating the value function and taking R plus next V, we'll actually directly estimate the Q function. The Q function is a function of states and actions. We can write down the same kind of recursion for computing Q. So for computing V, we took the reward plus the expectation of the next value, and the action that we plug in is the action according to the policy. When we estimate Qs, the Qs are a function of the state and the action. So what we do is we plug in both the state and the action, and then this part is the same. It's the expectation at the next state. This is actually a typo. This should be A, so probability of S prime given S comma A. But then for the value at the next state, we're going to plug in the pi, right? So when we plug in the pi in here, this gives us the value of the next state. So we plug in the pi here, and then we use the A here and here. So it's the same kind of recursion, just like what we had for value, except that now it's estimating a state action value function, or Q function. And the neat thing about this is that once we have the Q function, the maximization can be done without any knowledge of the system dynamics. So this is how we can do policy iteration with Q functions. And now, and this part we can fit, of course, using samples. And now we can do that max trick again. So this algorithm, this policy iteration that I wrote here is not actually an algorithm that we would typically want to use, but there's another one that we can derive where we apply that same max trick that we used to go from the policy iteration to value iteration. So we went from estimating V pi and updating the policy to just directly computing the max and updating the value. We can do the same thing with Q functions. So forget the policy, compute the value directly, and we can do it using Q values also without knowing the transition dynamics. And the way we do that is by writing down the equivalent fitted Q iteration algorithm. So before we had fitted value iteration, now we just have fitted Q iteration. Same exact thing, we compute target values, and then we regress onto those target values. Except that now, the computation of these target values does not have a max on the outside, because the target values are for a state and an action. They do have a max on the inside, because we need these V's. So in order to evaluate the V's, we'll just say that this is the max with respect to the action of the Q at the next state. The only reason this is an approximation is because this thing should be an expectation, and we'll just approximate it with one sample. So this doesn't require simulation of different actions because the Q function will already tell you the value for different actions. It's already baked into the function approximator. So you still need the max, but the max now doesn't involve trying different actions in the real world. It just involves trying different actions in your function approximator. So this works even for off-policy samples. I'll talk about that on the next slide. Unlike actor-critic algorithms, there's only one network, so there's no nasty high variance policy gradient. The downside of this approach, and we'll talk about this later in the lecture, is that there are actually no convergence guarantees for nonlinear function approximation. We'll derive some convergence guarantees for the tabular case, but when you actually use a function approximator like a neural net for this, a lot of guarantees go out the window. And this is something that we'll deal with also next week to derive a practical version of this algorithm. So now, does anybody have any questions about the procedure here, the fit acute iteration algorithm? Yes?
Sort of the same question. Is this maximization not tractable?
This maximization is tractable for discrete actions. For continuous actions, there are a few tricks that we have to do, and I'll cover those tricks next week. OK. So let's dig a little bit more into this fit acute iteration algorithm. And I'll write it out sort of in a longer format to have more of the details. So in fit acute iteration, we're going to have a number of different steps, and each of those steps will have some parameters that we can choose. So the first step, just like in all the other RL algorithms we'll be discussing, is to collect data. So in fit acute iteration, you're going to collect your data set using some policy. And the particular policy you use is actually up to you, because it turns out that nothing in the fit acute iteration actually assumes that your data came from your current policy. And we'll dig into this a little more. And you have to choose how much data you collect. So each time you collect your data, you can choose to collect either a tiny bit of data. If you collect just one sample, it becomes an online algorithm. Or you can compute a whole bunch of data, and it becomes more like a batch algorithm. Then you set your target values according to this rule. You set them to be the current reward plus the max of the next Q value at all the sampled states. And then you run your supervised learning to train your Q function to regress onto those target values. So your Q function is a neural net that takes in a state and an action, and it has parameters phi, just like before. And when you do this step 3, you can choose whether you want to train your network all the way to convergence, or you want to train it a little bit. Maybe you want to train for just one gradient step, a few gradient steps, or a huge number of gradient steps. That's a parameter of the algorithm. And you can repeat this process. You can actually bounce back and forth between these two steps a few times. Just like with actor-critic algorithms, every time you alternate between these two steps, you're essentially backing up your value one time step back into the past. So if you do it just once, starting from scratch, maybe you won't get a very, very good Q function. And maybe if you have a very long horizon, probably you want to do this many times. And then, so you get to choose the number of iterations k here, how many times you recompute your target values and redo the regression. And then eventually, once you're happy with it, you go back and sample more data. So this is sort of the high-level anatomy of pretty much any fit acute iteration algorithm. Does anybody have any questions about it? Yes?
Can this inner loop, step 2 and 3, can it be like sort of understood as something like an expectation maximization?
So the question is, can the inner loop be understood as some kind of expectation maximization? So we'll actually talk about a connection between probabilistic inference and reinforcement learning later in the course. So this will be around the time when we cover inverse reinforcement learning. And the short answer is yes. The long answer will be provided in about a month.
All right.
Any other questions? OK. So now I mentioned that this algorithm is an off-policy algorithm. Let's dig into what that actually means. Off-policy means that step 1 doesn't need to collect data from the policy that actually maximizes Q. It can actually collect data from any policy, although there are a few caveats as far as what policy would actually be good. And the reason for that is that nothing in these updates in steps 2 and 3 actually requires the data to come from your current policy. So the maximization, that computes the value of your current policy regardless of where this next state came from, right? So the value of your policy at the state S prime just depends on the Q value, and you know the Q value for all the actions, so you can just maximize over the actions. Even if the action that was actually taken in S prime was not the one that maximizes this, you can still evaluate the value of the action that does maximize it. And the transition here, so this approximates the value of pi at the state S prime without actually having seen the action A prime being taken. And the transition, so this is pi, And the transition here is also independent of pi because you're asking for a value for a state and an action. So you don't care whether the policy pi would actually ever take that action because you're going to learn a state action value function. So even if the actions in your data set, the a's over here, are not ones that your policy would have taken, it still doesn't hurt to estimate their value because you're estimating a state action value function. So for this reason, you don't actually need this data to come from the policy pi prime. It can come from wherever with a few important caveats that I'll describe a bit later. So one of the ways that you can kind of build some intuition for this is you can imagine that somebody just sampled a bunch of random transitions in the world. So somebody, plopped down the agent into a bunch of different random states. From each of those states, the agent took some action, that's the arrow, arrived at some other state, and you just got this bucket of transitions. Maybe the transitions came from some trajectories, so maybe they're not all disjointed like this, maybe they're arranged in a line, or maybe they really were just randomly scattered around in the world. You actually don't particularly care. You can just take this big bucket of data and run your fit-a-q iteration on it. So that's what it means to be off policy. Does anybody have any questions about this? OK. So now, a natural next question we might ask, now that we see that it's an off-policy algorithm, is, well, what is this algorithm really optimizing? Like, we have something in here that looks like a minimization of some error. What are we actually trying to do? Like, is there some objective we can write down? We had a really nice objective for policy gradients that was to maximize reward. And here we're like minimizing something, but this is not really trying to maximize reward directly. So the max, this is actually the improvement step. The max improves the policy in the tabular case. So if we enumerate the Q values at all the states and actions, this max is going to make our policy better. That's where the action is. But in the tabular case, of course, we don't even have step 3. So the step 3 is minimizing some error, and I'm going to call it E, because E is the first letter of error. And the error, what it really is it's the expectation with respect to states and actions distributed according to some behavior policy beta of this quantity, of the current value of the Q minus the target value, minus the R plus the next Q. This is sometimes referred to as the Bellman error. So if E is 0, that means that QSA is equal to RSA plus gamma max Q phi at S prime. Right, because if this difference is 0, then this equality has to hold. But it's equal to that under this expectation with respect to beta. So if beta has full support, meaning that there's a little bit of probability for all the states and actions, then having this error be exactly 0 means that this equality holds true everywhere. That's kind of a trivial case, but it's a very convenient trivial case because then, if this equality holds true everywhere, we can actually show, and I won't go through the proof in this lecture, but it's fairly simple to show, that this is what's called an optimal Q function, which corresponds to the optimal policy. So that means that if you take a policy that gives probability of 1 to the action that maximizes the Q, you can actually show that this policy maximizes the reward, meaning it's the best possible policy you can have, and it's sometimes this Q is written as Q star to indicate that it's optimal, and pi star to indicate that pi is optimal. So in the tabular case, where there's no approximation error, if E is 0 and beta here has full support, meaning that all states and actions have at least some probability on them, then you can show that the error being 0 means that the policy is optimal. But an important corollary to this is that beta really does matter. So imagine that beta gives 0 probability to all states in action except for 1. And then you perfectly minimize your Bellman error in that one state, but you're completely off everywhere else. Now, it's pretty obvious that at that point, unless that's the only state you ever visit, you can't really say anything about the performance of your policy in other states. So how wide the support of beta is really does matter. So even though the algorithm is off policy, it's quite a good idea to make sure that the policy that you're using to collect your data really covers the states and actions that you'll actually visit when you attempt to run the policy that corresponds to Q. And of course, most of these guarantees, as we'll talk about after the break, are going to be, well, that's really hard to see, are going to be lost when we leave the tabular case. So when we use neural network function approximation, unfortunately, these guarantees about optimality become pretty weak, and we'll see why that is in a second. But before we do that, let me just complete the derivation of these algorithms and derive the last algorithm, and the one that we'll actually spend most of our time on next Monday, which is the online Q-learning algorithm. So far we saw this fit-a-Q iteration algorithm, where we have the usual 3 steps. We collect the data, we compute our target values, we do our evaluation, then we do the regression to fit our neural net. But there's an interesting edge case of this algorithm where we set the number of data points in step 1 to be exactly 1, and then we do exactly 1 step of gradient descent here. Because when we do that, we actually get a fully online algorithm. So the online Q-iteration algorithm, which is also often referred to as Q-learning, works like this. You take one action, and you observe a transition, Si, Ai, Si prime, Ri. You use that one transition to compute a target value. So notice that this target value, all the symbols that appear here are the ones that you get here in this transition, so you can compute this target value. And then you compute the gradient of this error. So here I just computed the gradient for you. And then you update your parameters by doing a 1 step of gradient descent. So this is now a fully online algorithm. You get one data point, compute one target value, take one gradient step, and repeat. And this is the standard Q-learning algorithm. And just like the fit Q-iteration algorithm, this is actually a special case of fit Q-iteration. Step 1 is off policy. So you have many different choices for how you actually collect that data, although it's a good idea to get a distribution with pretty wide support. So how do we collect the data? Well, one thing we might do is we might say our final policy is going to give a probability of 1 to the action that maximizes the Q and a probability of 0 to everything else. So let's just do that, because that's going to be our final policy. Let's run this is sometimes referred to as the greedy policy. Let's run the policy that maximizes our Q, because once we're done learning the Q, this policy should be pretty good. So why is this a bad idea? Does anyone have any thoughts about why we might not want to do this? Yes?
Maybe we're going to get stuck in one state. Like there's one state we will think at the beginning of the algorithm looks good, and we'll never explore the other ones.
Exactly. So the answer was that we might get stuck in some state, decide that that state is good, and we just keep going there repeatedly, and we never try anything else. So this policy is called the greedy policy for a reason, because it greedily exploits the current Q function. So if your Q function is not yet good, let's say you saw your first ever reward, and you decide, well, this reward is great, I'll just keep going for that, and I'll never try anything else. There might be some big mountain of reward right on the other side that you would just completely ignore. So this is a part of a larger problem in reinforcement learning that we'll have an entire lecture on later on called the exploration problem. But for now, let me just tell you about a few standard things that people often do in Q-learning algorithms that are kind of simple heuristics that oftentimes do a reasonable job of getting around this problem. So one very simple heuristic is to say, this policy is pretty good. I'm pretty happy with that policy, but I just don't want to completely commit to it just yet. I'll commit to it up to some little factor epsilon. So with probability 1 minus epsilon, I'm going to take the optimal action. But there's always that small probability that I'll just do something else. And the way that you do something else is, well, maybe you just say all the other actions are equally likely, so they get probability of epsilon divided by the number of actions minus 1. So with probability 1 minus epsilon, I'm going to take the best action, and with probability epsilon, I'll sample uniformly at random from the other actions. This is a very, very standard common heuristic for exploration in Q-learning that's called epsilon greedy. It's largely a heuristic, but it's really, really simple for discrete action spaces and tends to work reasonably well for many problems. A slightly more nuanced choice of exploration strategy is what's sometimes called Boltzmann exploration. The intuition behind Boltzmann exploration is that the Q function more or less knows what's good and what's bad, but there's some amount of uncertainty. So if the Q function is really sure that something is a really bad idea, just don't do it. But if it thinks that two things are about equally good, maybe you do them with about equal probability. So in Boltzmann exploration, what we do is we construct a probability distribution. I'm sorry, there's a typo here. There should be A given S, not A given A. In Boltzmann exploration, we construct a distribution where the probability of taking different actions in a particular state depends on their Q value. And a very common choice here, you obviously need to convert the Q values into probability, so they need to be positive and need to sum up to 1. One very common choice is to make them proportional to the exponential of the Q value. So this does a really nice job of breaking ties, because if two actions have pretty much the same value, they get equal probability, but as they become worse, they become exponentially less likely. There's other transformations you can use other than an exponential, but it actually turns out that the exponential transform will lead to a very interesting connection between reinforcement learning and probabilistic inference that we'll derive later on in the course. Okay, so we'll discuss exploration in more detail in a later lecture. But for now, does anybody have any questions about the online Q-learning algorithm or these simple exploration heuristics? Yes?
How would you use these exploration heuristics in your final policy rather than just during your policy training picking?
So there's typically no advantage to using them for your final policy. When you're done learning, you're usually better off doing this. In fact, you can actually show that in a fully observed environment, meaning that you get to actually see the states rather than observations, the optimal policy, there will be a policy that is as good as the optimal policy that is deterministic. So there's no benefit to having a stochastic policy at the end if you've really learned the true optimal policy. But while you're learning, this kind of stuff can really keep you from getting stuck. Yes?
Can this exploration, this epsilon greediness, affect your convergence?
Yeah, so the choice of exploration very strongly affects convergence of Q-learning algorithms because it affects the support of beta. So remember that even though the algorithm is off policy, the support of beta really matters. Any other questions? Yes?
What about if you put maybe this will be a little more, I guess, esoteric. But what if you put like a reward for expectation and the reward exploration and the reward function?
Yeah. This is actually a lot of what we'll discuss in the exploration lecture, that many of the methods that incentivize exploration that are more sophisticated, they do something that looks like adding a pseudo-reward for visiting new states. And there are many ways of doing that, range from very simple to very nuanced kind of Bayesian approaches. So we'll talk about those later in the course. All right, let's take a, let's review first and then we'll take a little break. So we talked about value-based methods that don't learn a policy explicitly. They just learn a value function or a Q function. If we have a value function, we essentially have a policy because we can extract a policy from a value function. We talked about fitted Q iteration, which is this sort of class of algorithms where we have a number of choices for different parameters. It can be it's a batch mode off policy method, but we can actually derive, for a particular setting of those parameters, an online algorithm, which is called Q learning. So that's what we covered in the first half of the lecture, and now we'll take a 3-minute break. And after the break, we'll talk about some theory. Yes?
Back to the slide with the online queue.
Confused about the terminologies.
Uh-huh.
So, what's the like? How's online algorithm and like off policy algorithm related? Like, do online algorithms have to be off policy or?
No, so we actually had an online actor-critic algorithm on Monday, and that one was on policy. So the two decisions are not actually related. You can have online off policy, online on policy, and so on. Online just means that you're getting data, you're consuming that data, you're getting more data, and so on. So everything's kind of streaming.
Like stochastic role-playing game.
Well, the batch mode algorithms are stochastic also. It's really the fact that this like a streaming algorithm that you're learning as you're getting more data and you're throwing out the data once you've learned with it.
I see, but you could also like, if you're doing parallel like simulations and stuff, you could get like 4 online.
That's right, yeah. So the online actor critic that we discussed on Monday, actually, the version of that tends to work well is actually one where you do have parallel collection for larger batches.
But how is it different from small batch? Like, how is online different from small batch?
Well, online refers to how you're processing your data, not how you're taking gradient steps.
Okay, I see.
I had some laptop issues and I was unable to submit my stuff on Monday.
Okay. Just send an email to me and to the TAs.
Okay, I can submit it today.
Well, just send us an email.
Okay.
I just don't have time to discuss this right now. It works? Okay. And is that showing up on the?
Yep.
Okay, excellent. All right. Okay, let's continue. So before the break, we saw how we can derive an online Q-learning algorithm. And now, for the remainder of today's lecture, we're going to study how this algorithm works and what kind of properties it has. And we'll actually, to start with, we'll back up and we'll deal with just value iteration algorithms, but we'll come back to Q functions as well. So this is the value iteration algorithm that we saw before the break. And it just consists of computing the Q function and then maximizing the Q function. So in this little tabular setting, where you can write down the value of every single state. And a very natural question you might want to ask, in fact, this is a good question to ask anytime you see something that someone claims is an optimization algorithm. A good question to ask is, does it converge? And if they tell you yes, then you ask, what does it converge to? So if it does converge, does it actually converge to something you want? There are algorithms that converge to things you don't want. So let's think about this a little bit. Let's think about how we can work with this algorithm. To do that, we'll first define an operator called B for backup. And what this operator does is it evaluates the max, and I'm using vector notation here. It's going to evaluate the max of the Q function at every state. So the notation here is that this RA, this is a big vector where every entry in that, there's one entry for every state, and the entry that you get from that state is the entry for the action A. So this max is a per element max. And this TA, this is a matrix. If this is like a 16-state grid world, it's a 16 by 16 matrix of transitions for the action A. So for every single transition, we choose an action A. That's what we're maximizing over. And that gives us this matrix where ij is the probability of being an I given j and the action A. And then the V is just a stacked vector of the values at all the states. So I've just rewritten these things with matrices and vectors. So this maximization, this is an operator that we can apply to V. And we can just say BV is the max of this thing. And using this notation, we can actually show that the best value function, the V star, is actually a fixed point of B, which means that if you have a value function that is equal to the reward plus the expectation of the next value, that just means that V star is equal to B times V star. So this is just a tautology, right? So B is basically the thing that computes this backup. So if these are equal, that means that V star is equal to B times V star. So there is a fixed point of B, and that fixed point is pretty damn good because it's the value function for which the reward, which is equal to the max, there should be a max here, of the reward plus the next value. And just like we discussed before, this is going to correspond to the optimal policy. You can actually show that this fixed point always exists, it's always unique, and it always corresponds to the optimal policy. I won't show that on this slide, but this is basically the same as with the optimal Q function. The question that we really want to understand is, will we reach that fixed point? So it's relatively uninteresting to say that this fixed point exists. It's also not that hard to show, but the question that's really interesting to us is, will we actually find that fixed point? So if we find the fixed point, we know that we're happy, we have the optimal value function from which we can extract the optimal policy. So now let's think about whether we'll actually reach this fixed point using this funny algorithm. So again, we're going to consider just the tabular case. V star is a fixed point of B, and that's what we had on the previous slide. And it turns out that we can actually prove that value iteration reaches V star, and the way that we can prove that is by showing that B is a contraction. So what it means for B to be a contraction, it means that if you have two value functions, V and V bar, and you apply B to both of them, then the distance between these two value functions, and remember, for the purpose of this discussion, a value function is just a vector of numbers. The distance between these two value functions after they've both been transformed by B is less than or equal to the distance between the value functions before they've been transformed. In fact, it's actually less than or equal to their distance multiplied by gamma, by the discount factor. And it's important to note that this distance is with respect to a particular norm, and the particular norm for which B is a contraction is the infinity norm. That just means the largest entry in that distance vector is going to be less than or equal to what it was before times gamma. So you're going to decrease that distance by a factor of gamma. So the gap always gets smaller by gamma along the largest, the most violated dimension. Again, I'm not going to go through the proof of this, but those of you that are interested, if you ask me afterwards, I can point you to the proof. It's not exceptionally exciting. It's just a bunch of algebra. But you can show this. You can show that B is always a contraction with respect to the infinity norm. So now it's pretty easy to show that value iteration converges. We just say, well, let's pick V bar to be V star. And remember that V star is a fixed point of B. So when we apply B to V star, we just get V star again. So now we just plug that into this equation for the contraction. And since B times V star is just V star, we just get BV minus V star is less than or equal to gamma times V minus V star under the infinity norm. So that means that every time we apply the operator B to V, we get closer to V star with respect to the infinity norm. So we start off far from V star, there's V star, and we're going to gradually get closer towards it, and each time we get closer with respect to the infinity norm. So this is a sketch of how we can prove that value iteration converges. At a high level, the way we prove it is by introducing the operator B, proving that B is a contraction under the infinity norm, proving that there exists a fixed point V star, and then we'll know that we actually reach V star. Does anybody have any questions about this? Yes?
What about the rate of convergence?
Yeah, so there's the rate of convergence. You can kind of guess on an upper bound from this gamma, right? So if you're getting closer by gamma each time, you're going to converge faster. And there's a very natural intuition behind this, because gamma controls how much does the future matter. So if the future matters not at all, it kind of makes sense that you converge right away as soon as you memorize the rewards. So the smaller the gamma, the faster you'll converge. Yes?
What if the task is undiscounted?
If the task is undiscounted, then the analysis gets a little different. So if the task is undiscounted and you have finite horizon, then actually you will converge in a number of steps equal to the horizon. It's just a standard dynamic programming formulation. For average reward, it gets a little more nuanced. All right. So now let's talk about the case that we really want to know about, which is the non-tabular case, the case where you're going to be fitting a function approximator to the value function. So this is our really, really tiny value iteration algorithm using B. And now we want to write down the fitted value iteration algorithm, where we now have a function approximator, but in this nice form again. So in the fitted value iteration algorithm, the thing that we introduce is the second step where we do the regression. So what is this regression really doing? Can we somehow abstract it away into a mathematical object that we can analyze a little more easily? What does this do? Well, it computes the argmin of value functions in some class of value functions omega that minimizes this error. So what this means is omega maybe is the class of all functions you can represent with a neural network that has 2 layers and like 100 hidden units. So omega is your class of functions. And when you do supervised learning, you're searching for a function in your class of functions that minimizes your loss. This is my loss. This is just the function I'm learning, v prime, minus the backed up version of my last value function. And I'm searching for this v prime within the class omega, which, if you have neural nets, maybe is the class of all neural nets with 2 layers and 100 hidden units. So that's, at a very high level, an abstraction of what supervised learning does. Assuming that you don't have any problems with non-convexity, assuming that supervised learning exactly solves that minimization, it's doing this. So all value functions, for example, the class of all neural nets. So you can imagine this graphically. Let's imagine that this blue line, so that this space here is the space of all value functions. And remember, if you're in a discrete environment, the space of all value functions is actually just a space of vectors of a fixed size with 1 entry for every state. So it could be actually a finite size space. And this blue line is the space of all functions in omega. So omega, neural networks in general, infinitely large neural networks are universal function approximators. They can represent anything. But finite size neural networks are finite. So there are some things they can represent, some things they can't. In reality, if you have a non-convex optimization, maybe it's going to hit a local optimum. So there's some space of things that you can plausibly get when you do this minimization that is a subset of all the possible functions. And that's represented here by this blue line. So when you perform the backup, when you compute b times v, so this is a set of neural nets. When you compute b times v, you step off of this manifold of function approximators. And you step off of that manifold in such a way that brings you closer to the optimal value function with respect to the infinity norm. When you perform this minimization, you're projecting yourself back down to the manifold, because you're trying to find a new value function v prime that is within the set omega. So that means that we can define a new operator, capital pi, where pi is the projection operator. So pi takes some value function, any value function, and it finds the closest value function in the set omega, closest with respect to what? Closest with respect to this error. And this error is Euclidean distance. So this is an L2 projection onto the set omega. So that means that we can now write down the fitted value iteration algorithm, again in one line, as just the composition of 2 operators. You take your current value function, you apply b to it to back it up, and then you apply pi to it to project it. So you can also call it projected value iteration. You back up your value function, and you project it. And that's mathematically all of this algorithm is doing. But now we can do some interesting analysis. So this is our fitted value iteration algorithm using B and pi. B is a contraction with respect to the infinity norm. That means that the largest entry in the difference between the two value functions is going to go down. That's what infinity norm means. And this is how we can write it out. Pi is a contraction with respect to the L2 norm. Any projection is a contraction with respect to the L2 norm. You can very easily visualize this. Imagine that we have these 2 points. We're projecting them onto a line. They're not going to get further away from each other. So you can draw a triangle. There's a triangle with one leg here, and a hypotenuse. This leg basically gets deleted, so they get closer together. So anytime you have a projection, it's a contraction with respect to the L2 norm. OK, so both of these things are contractions. That's pretty good, right? The trouble is that when you compose them, when you compose pi and b, it's actually not a contraction of any sort whatsoever. And the reason for that is that they're contractions with respect to different norms. So this is a contraction with respect to the infinity norm, and this is a contraction with respect to the L2 norm. And that's bad news, because it turns out that if you compose these two contractions with respect to different norms, their composition is not a contraction with respect to anything. And we can kind of visualize this graphically also. So what we'd like to do is we'd like to always have a contraction so that we walk towards the optimum. But what we're going to do instead, let's say this is the optimum. We perform the Bellman backup. That's a contraction with respect to the infinity norm, so it gets us closer with respect to the largest dimension of error. And then we perform a projection. The projection basically puts us down here at a right angle, right? So the projection can actually move us further than when we started. So even though each step of this gets us closer to the target with respect to some norm, the composition of these two steps can actually bring us further away from the target with respect to both of the norms. So repeatedly applying fitted value iteration can actually move you away from the optimum. It can also move you towards the optimum, and it can also move you pretty much anywhere else in between. So that's kind of bad news. So some conclusions, some unfortunate conclusions about the harshness of the real world. Value iteration does converge in the tabular case. Fitted value iteration does not converge in general. Not in general, and also not in practice oftentimes. Yes?
Why is BV outside of omega? If your neural network can approximate any... Okay,
so an infinitely large neural network can.
Yeah, so if it's infinitely large, then you wouldn't have this problem.
So what you can do is you can actually derive a class of function approximators for which this problem doesn't exist. Oftentimes, this kind of analysis is done with non-parametric function approximators. You can actually derive non-parametric function approximators where provably the composition of the projection and the Bellman backup is a contraction. But for an arbitrary class of function approximators, in general, their composition is not a contraction. And with neural nets, the real story, there's always like the textbook story that you learn about, and then there's the real story, which is a lot more complex. The real story is that with neural nets, even if they can represent a very wide class of functions, when you actually practically optimize those neural nets, the inductive bias of the network will give you a solution that's going to have some error. So essentially, this problem doesn't exist in a few cases. One of those cases is where the projection is errorless. So if you project with a training error of 0 and no sampling error, meaning perfect extrapolation, then you're golden. But the chances of you being able to do that with a parametric function approximator are not high. Now that said, these kinds of questions can lead us to good intuition about how we can mitigate these issues. So we typically can't solve them completely, but we can mitigate them. And that's a lot of what we'll discuss actually next Monday, is some practical tricks that can mitigate them. But it's important to remember that in general, function approximation plus Bellman backup is bad news. Any other questions about this? Yes?
Why don't we have similar issues for policy optimization?
Right, so the question is, why don't we have similar issues for policy optimization? The reason is that policy gradient is a well-defined gradient-based optimization on the objective that we care about. So policy gradient is actually taking gradient steps on the expected reward. This algorithm is not taking gradient steps on anything. So that's the underlying issue. So gradient descent or gradient ascent, we know that it converges. We know how it converges and all that stuff. So we can apply that analysis to policy gradients. Yes?
In general, like if we're doing, when we do we chose the L2 norm, right?
Mm-hmm.
Could we choose another norm that might perform better?
Yes. The reason that we chose the L2 norm is because it's tractable to formula optimizations that way. So when you might say, okay, well, if this is infinity norm, are we in good shape? But what does it really mean for this to be infinity norm? If this is infinity norm, that means you're going to go out and find the state that has the largest error in the value function, and you're going to minimize that. Now, finding that state is really, really difficult if your state space is large or infinite. All right. Yes?
What would be the optimal, so for example, if this were converging on the manifold that the function can actually learn, which point would we prefer the most? Is it the end to projection?
So typically, when we do this kind of analysis, what we say is that, well, okay, so what the question, by the way, for everybody else, what the question is getting at is this star is not on the manifold. So then one might ask, well, is this even like a well-defined, like is it even well-defined to ask how well do we do? So we have to choose some other notion of optimality than saying that we'll reach star, because reaching star is clearly impossible no matter how you optimize. So usually when we study these algorithms, what we say is we want to find the projection of the optimal value function. So we take the star, we project that down onto the manifold, which will be somewhere over here, and we say we want to reach that, because that's the best we can hope for from our function class. That, by the way, is analogous to how we study policies. Like with policies, we don't actually hope the policy gradient will find the best possible policy, just the best possible policy in our class. Okay, what about fitted Q iteration? So far I talked about these value iteration algorithms. What about Q iteration? Well, it turns out that with Q iteration, it's exactly the same. So with Q iteration, I can define an operator B. The B operator is a little different, right? Before the max is on the outside, now the max is inside this multiplication. So now it's after the transition operator, but it's still a well-defined operator. It's still a nice, convenient operator. And in fact, it's still a contraction. I can define the projection pi. The projection pi is still exactly the same projection, except that now it's with respect to state action value function instead of functions of just the state, but still exactly the same idea. And I can still show that you can do your fitted Q iteration with this pi times b. B is a contraction in the infinity norm, pi is a contraction in the L2 norm, and exactly the same analysis applies. So this also applies exactly the same way to online Q learning, to fitted Q learning, and so on. So all these algorithms suffer from this issue, which is that when you do the backup, that gets you closer with respect to the infinity norm. When you do the projection, it gets you closer with respect to the L2 norm. And we do both of them, who knows what the hell happens. So that's the trouble. Now, some of you might have noticed when you saw the online Q learning algorithm that there's something a little suspicious going on. Like we have this thing here, and this is a gradient. I actually derived it here for you. It's the gradient of the Bellman error. So, okay, there's all this stuff about projections, but in the end, like this is a gradient, and if this is just gradient descent, surely that must converge, right? Because gradient descent converges. Does anyone maybe see a problem with this kind of argument? Yes?
Can you think of the Bellman operator as a regularization term?
Can you think of the Bellman operator as a regularization term? Not exactly. I mean, the Bellman operator, it actually changes your value function. It gets you a new value function that's closer to the true one. So it's not really a regularization. It's an optimization step. Yes, back there?
So here the value of yi is constantly changing, which is the target that we're trying to approximate.
That's right. So what the comment there was, for those of you that didn't hear it, is that the trouble with this equation is that this y, it's changing. So this is a gradient, and this is indeed the gradient descent update, but it's a gradient descent update on an objective that keeps changing. So Q learning is not actually gradient descent. In fact, since this y depends on Q, if I was honest in taking my derivatives, I would actually have pushed the gradient through that too. That has a whole host of other problems that we can talk about after the lecture. But as written, this algorithm is not gradient descent. It has an update that looks an awful lot like a gradient descent update, but it's fooling you. It's not actually gradient descent. It's this funny projection. So this is, I can write it out. I can substitute this thing in for the y, and you can see that there's this thing here, and there's no gradient through that term. So it's not gradient descent. There's kind of sort of a sad corollary to what I just discussed, and that sad corollary applies also to something that we went through on Monday. So on Monday, we went through the batch vector critic algorithm, and in the batch vector critic algorithm, you also, in step 2 here, when you fit the v hat, you compute these target values, and you minimize some error. And that has the same problem. So this is your backup. Now the backup is not doing a maximization, it's just a backup for a particular policy. And this is still an L2 projection, but the same issues hold. So this is a contraction in the infinity norm, this is a contraction in the L2 norm. The fitted bootstrap policy evaluation doesn't converge. So even though this is what I told you all guys to use on Monday, it has all the same problems. And on this subject, a little aside regarding terminology. So in the actor critic slides, I used vpi everywhere. So vpi is the value function for the policy pi. So this is what the critic does. And v star is the value function for the optimal policy pi star. So this is what value iteration does. So if you ever see v pi versus v star, someone tells you I'm fitting v pi or I'm fitting v star, what they mean is that it's basically whether or not there's a max in here. Are you trying to fit the optimal value function or just the value function that corresponds to your current policy? But whichever one you're trying to do, if you're doing it like this, you're still in trouble because this in general is not guaranteed to converge. So that's our sort of sad conclusion from today's lecture, and then we'll have some happier conclusions on Monday. Does anybody have any final questions about the convergence of Q-learning and value function fitting? Okay, let's summarize what we learned in the second half of the lecture. We talked about some of the theory behind value iteration, how there's a linear operator for the backup, how there's an operator for the project. It's actually not a linear operator in general, it's a lie. The backup is a contraction, and the projection is a contraction, but nonetheless, when you compose them, it's not a contraction, and value iteration does not converge. We talked about, it doesn't converge. And some of the implications for Q-learning, that Q-learning, fitted Q iteration, et cetera, doesn't converge with function approximation. But we'll actually be able to make it work in practice with some hacks and some tricks, and those we'll cover on Monday. See you then.